Hello, today we are looking at volume by slicing in section 6.3. So if you remember back from Calc 1, you did area of regions. Well, this is a very similar argument. So basically what we're going to look at here is if you have a surface and you can divide it up in such a way that all the cross sections are basically the same shape. So this happens with some surfaces and doesn't happen with others. But if you have a similar cross section and you can write an expression for the area of that cross section, then you can basically just sum up the volume of all these little slices. So I would take the area and multiply it by a little dx and then sum all of those up. And we could get really complicated and talk about Riemann sums and how to set up all these intervals and everything. But it's exactly an argument you saw in Calc 1 and that you'll see more times going forward for why this turns out to just be an integral. And basically what we end up with, you can see right here, is the integral from a to b of capital AX dx, where AX is the area of one of the little cross sections. So there we are, the general slicing method. Let's scroll down and take a look at, in the homework, question number 8. We want to find the volume of the solid whose base is the region bounded by the semicircle, y equals the square root of 1 minus x squared, and the x-axis, whose cross sections through the solid perpendicular to the x-axis are square. So if this is square, then we know that one side has length y equals 1 minus x squared. So that actually means since it's square, it's 1 minus x squared is the length of each side. So that makes the area of one of the cross sections 1 minus x squared. When you multiply those, you get 1 minus x squared. So what we want to do then is integrate 1 minus x squared from, well, we need to know what our range on our x values is going to be here. Well, it's going to go minus 1 to 1. That's when you hit 0 here, right? If you put in 1, you would get 0. If you put in minus 1, you would get 0. So we're integrating minus 1 to 1 of 1 minus x squared dx. And actually, I did that over here. And you get x minus x cubed over 3 from minus 1 to 1. You end up with 2/3 minus negative 2/3. When you work that out, that turns out to be 4/3. Now, the other problems we're going to do in this section, you could do with this general slicing method. It would work, but it turns out there's a little bit of a shortcut for some of these, so that's where these other methods come in. The first method we're going to look at is called the disk method. And basically, the disk method comes about when you take a curve, and it's above the x-axis, and then you revolve that curve around. You can see this happening over here. If we revolve this curve around, we create a surface of revolution. And there they're just showing you the cross section. But if you move, you can see all the cross sections. Right? And we can create this three-dimensional shape that way. Well, we could do the same thing. Just find the area of the cross section and integrate. But we know here that the area of the cross section, because they're circles, and the radius of the circle is, well, here it is f of x, right? Because this goes from 0 to f of x. So whatever that is, that's the radius. And what's the area of a circle? Well, it's pi r squared. So basically, we're looking at our volume here is the integral a to b of pi f of x squared dx, for whatever that function is. So that's pretty straightforward. So we'll look at a couple more examples there. We're going to look at number 18. Actually, let's go look at the problem before we hop over here. So problem number 18 wants us to use the disk method to find the volume of the solid generated when r is revolved about the x-axis. So you can see here, we've got y is 2 minus 2x. We want to revolve that about the x-axis. So when we do that, we end up integrating, well, pi f of x squared dx, and we're integrating 2 minus 2x squared because our function was 2 minus 2x, and we're integrating that from 0 to 1 on the x-axis. So 0 to 1, that's our integral. I went ahead here and I pulled out the 2. It becomes a 4 when you pull it out of the square. So I'm just integrating 1 minus x squared, which I expanded that first and then integrated each part, plugged in at 0 and 1. All the zeros disappear on this one, and you just end up with 1 minus 1, which disappears. And then this is 1/3, so you end up with 4 pi over 3. Okay. The next thing that we're going to look at is number 36. And this is just doing this about the y-axis. Well, the formula just changes, right? So our formula that we had previously, we had the disk method about the x-axis. Well, for the y-axis, it just changes. You need an f of y dy is basically all that changes. And then we need our interval to go from y equals something to y equals something. So on number 36, what we need to do is we need an f of y. So right now this is like f of x is natural log of x. So we need to solve this thing for x basically. So this is going to be x equals e to the y. So our function is going to be f of y is e to the y. And then we see our range on the y-axis that we need is 0 to 2. So if we take a look, we're integrating 0 to 2, e to the y squared dy. Well, the integral of e to the, that's the same thing as a e to the 2y, right? And that integral is 1/2 e to the 2y. And we're evaluating that from 0 to 2. Well, when you plug in 2, you get e to the 4th over 2 times pi. And when you plug in 0, you get a 1 out of this because e to the 0 is 1. And then pi over 2. So we have e to the 4th over 2 pi minus pi over 2. So that is number 36. The last thing that we want to look at today is the washer method. And again, this would also work with the general slicing method. But when the washer method comes up, is if I'm looking at two curves, and I want to revolve those around either the x or the y-axis and find the volume of the surface that we get from doing that. Well, the cross-sectional area here, basically we're going to get that by taking, well, this thing's called the washer method because basically what you're doing is you're going to subtract the area of the big circle minus the area of the little circle here for cross-sectional area. So it becomes just our formula that we had for the disk method, but we do the outside function minus the inside function so that we're taking the bigger disk, the bigger circle, minus the smaller circle, and that gives us the area of this washer. Right, so our washer formula is just f of x squared minus g of x squared dx. And then we've got the pi in there too, right, because again, these are circles. We're finding the cross-sectional area. So, the problem I chose to do for that one was number 27. So let's take a look at number 27. We're supposed to do the washer method. Y equals x, y equals 2 root x. So here's our bigger function, I guess, the one that is our f of x. This is our g of x. So if we take a look at the work for this, here's our formula we're going to use. In this case, when you square 2 root x, you get 4x. If you square x, you get x squared. We're integrating 0 to 4. How did I find that? Well, you find the places where these intersect. So they intersect at 0, and they also intersect at 4. You could use algebra to find that. You could see it on a graph or something. But that's how you get to there. Then you integrate those, plug in at 0 and 4, and it turns out to be 32 pi over 3. Okay, that is going to be it for this video. I hope that is helpful in using the general slicing method, the disk method, and the washer method to find volumes of surfaces.